I'll summarize again Bloch's theorem. So we have an Hamiltonian where the potential is periodic with respect to a Bravais lattice. Okay, so that's the assumption. And we're looking for solutions of this Hamiltonian. And we label solutions according to a number, to a quantum number k. So solutions can be labeled by k belonging to the Brillouin zone. And second statement, psi k of R can be written as uk of R e to the I k dot R, where this is a periodic function. Okay, periodic, of course, with the same periodicity as the potential. Okay, so that's the hypothesis, and this is the thesis, what Bloch's theorem states. Notice that here I'm saying can be written, not must be written, can be written. You can write it in different forms, but whatever way you write it, you can actually rewrite it in terms of in this particular form. I mean, an example was the function we determined last time as a solution of our one-dimensional problem. It wasn't obvious that the solution could be written in this way, but actually it could. We managed to write it in this form just by algebraic manipulation. Okay, just a minor consequence of this. The function, again, we discussed last time, the solutions do not need to be necessarily periodic. Okay, so solutions of an Hamiltonian which has a given symmetry don't need to maintain that symmetry, to have the same symmetry. However, they have these important properties. There is, however, an exception here, and this is the point where k equals to 0, the center of the reciprocal space. The center of the reciprocal space, k equals to 0. K is equals to 0 here, so the solution is periodic. So there is one particular point in the Brillouin zone, and that's the center k equals to 0, in which the solution is indeed periodic and has the periodicity of the lattice. But that's, of course, an exception. Everywhere else, this phase here is not commensurate with the lattice. So actually, let me make a couple of remarks here. So A, if k is equal to 0, psi of k, which is equal to 0, of R, is indeed periodic. Just as a consequence of what we just said here. It's a sort of remark that follows naturally from Bloch's theorem. Let me make another remark, which we already made last time when we discussed the one-dimensional, about the necessity, about the need to go outside the Brillouin zone. Let me recall what the Brillouin zone is. The Brillouin zone is the Wigner-Seitz cell in reciprocal space. So once the Bravais lattice is defined, we can define a reciprocal lattice. Okay? Once we define a reciprocal lattice, we can define unit cells. The Wigner-Seitz unit cell in reciprocal space is the Brillouin zone. So we are now working in, when we talk about K, we are working in reciprocal space. So, and when we say that K belongs to the Brillouin zone, we say that we're not really saying that K must be inside the Brillouin zone. According to the discussion we made last time, K in principle can be outside, but there's no need to go outside, because if we go outside, we find solutions which are already present inside the Brillouin zone. Okay, so let me now evaluate that statement in this more general context. So suppose, okay, I define a wave function, I define a psi for a k which is outside the Brillouin zone. So suppose that I consider a given k, and I consider it that does not belong to the Brillouin zone. Let me see what happens if I move outside the Brillouin zone. Okay, k does not belong to the Brillouin zone, right? So it's not inside the Wigner size unit cell. If it's not in the Brillouin zone, it must belong to another unit cell, centered at another reciprocal lattice point, right, which is not the origin. Okay? So when I say this, that implies that k, it must be possible to write k as a vector g, a reciprocal lattice vector, plus a vector which is inside the Brillouin zone. Right? Whatever is outside the primitive, the Wigner size unit cell centered at g equals to 0, must be something that I can express as first I go to the reciprocal lattice point, and then I move inside that local Wigner size cell to reach my particular point. Okay, we discussed this already. Yes?
You were saying that psi is a function of k which belongs to the Brillouin zone.
Well, the psi is not really a function of k. This is a parameter. The psi is a function of r. It's a wave function. But you can label different psis according to index k. So it's a parameter more than a function of k.
Okay, because what could cause me k Brillouin zone and then
K, sorry, k?
belongs to the Brillouin
Yes.
zone.
K belongs to the Brillouin zone, yes.
Yes, and then down there you are writing psi as a function as a periodic part, which is periodic in the
Sorry, periodic in R.
yes, which is in the other lattice space.
Yes, so it's periodic according to the Bravais lattice. So it's like V, essentially. It's something that is periodic with respect to the Bravais lattice. Okay, so this function, not just, all these functions of k, all of them, for all k's, are periodic in R, with the periodicity of the Bravais lattice. Okay? You have to be careful because there are two periodicities here. One is the periodicity in real space, and the other is periodicity in reciprocal space. So you always have to be careful about what you're talking about here.
That's why I'm confused because we have those two.
Okay, so the best way to think about it is to think that all our functions are functions of R. So they're defining real space in R3, real space. However, there is a different function for every k. And k is an index that is a continuous index and runs over the reciprocal space. Okay? So in fact, I always try to avoid the statement that these are functions of k. Although, in practice, you can think of them. Suppose you fix R. This is a function of k, of course, because for different k's, you have different numbers. But I try to avoid this terminology because these are actually functions of R, and they're just labeled by k. So different k's give you different functions. Okay, so let me consider, for example, that k does not belong to the Brillouin zone. What happens? So if k does not belong to the Brillouin zone, I hope you're all by now familiar with this, but let me, just for the sake of clarity, suppose this is the reciprocal lattice, okay? We're working in the reciprocal lattice. This is the Brillouin zone in reciprocal space, right? Ky, kx. That's a square lattice, of course, right? This is 2 pi over a, this is pi over a, and all that. That's the Brillouin zone. If I have a point that lies, say, here, outside the Brillouin zone, obviously, I can write it as a g plus a small vector that belongs to the Brillouin zone, right? This is a small vector that is inside the Brillouin zone. In other words, I have to translate my origin here, and then I move inside the Brillouin zone, centered at that point. Okay, that's the meaning of this. If a point is outside the Brillouin zone, I can reach it by first moving with a big jump on the reciprocal lattice vector, and then close to that reciprocal lattice vector, I can use a vector of the Brillouin zone. Okay, but if this is true, then my function it will be possible to write it as e to the I g dot r times e to the I k Brillouin zone dot r. Okay, because if k can be decomposed, I can decompose the exponential part in that form. But now let me take a look at this function here. This function is periodic with the periodicity of the lattice, the Bravais lattice. What about this one? What if I take e to the I g dot r plus an arbitrary Bravais lattice vector? What happens to this function here, this part of the function? If I try to translate it by a Bravais lattice vector. Reciprocal lattice vector, Bravais lattice vector. This is 1, right? So this function is also periodic. Okay, that's actually a very important statement that we'll use several times in the future. A plane wave where G is a reciprocal lattice vector, it's one of the vectors of the reciprocal lattice, is a periodic function. If G is not a reciprocal lattice vector, say it's a K, for example, in the Brillouin zone, this is not a periodic function, of course. But if the plane wave has the reciprocal lattice vector, then it is a periodic function, for an obvious reason. Because if I translate it by a Bravais lattice vector, this phase here is 1 by definition of a reciprocal lattice. So this function is periodic. This function is also periodic. The product is a periodic function. So in other words, I've expressed the same function in terms of a periodic function and the phase where k belongs to the Brillouin zone. That's exactly what Bloch's theorem states. Notice that I've taken advantage of the fact that Bloch's theorem states that I can write the wave function in that form, not that I must write the wave function in that form. Okay? So it was possible for me to write the wave function even if k was outside the Brillouin zone. It has been possible for me to rewrite the wave function in a way that contains a periodic function and the phase with k equals to the Brillouin zone. That's exactly what Bloch's theorem states. So I can, not I must, I can use this number, this vector, to label my wave function. I don't need to go outside the Brillouin zone. Because I've been able to write it in a form that is consistent with Bloch's theorem and k belonging to the Brillouin zone. I understand the logics is a bit difficult to digest, but that's the way it is. I just wanted you to get a little bit more familiar with this. Okay. Any question about this? No. Great. Let me now continue and try to find ways to solve my problem. After all, this is just a theorem that states what the wave function looks like, but it doesn't really solve my problem because it just translates the problem of determining psi into the problem of determining u, right? It doesn't really solve my problem. I simply change the target of my search. If I want to solve this Hamiltonian and find psi, what Bloch's theorem tells me is simply that I can write it in this form. It doesn't say what u is, right? So I'm just transforming the problem into the problem of solving this Hamiltonian into the problem of determining this periodic function, u. Okay? However, I hope you realize that this kind of help is extremely useful. There is one important reason why this is extremely useful, and this is the following. Psi, in principle, is a function defined over the whole space and can take any possible value, right? It's a function defined in R3, period. We don't know anything else about it. As soon as we introduce Bloch's theorem, we transform the search for a generic function defined in space into the search for a function that is now periodic. Okay? What periodic means is that I can define that function within the unit cell, for example, for r's inside the unit cell, and once I define it inside the unit cell, I'm done, because I know it's periodic. Okay? So I've restricted the search for my wave function from the whole space into the space of the unit cell, which is a finite region of space. All right? Now, this is a tremendous simplification because I can work with a finite space. I don't need to work throughout the space. I can simplify the search considerably. I just need to search now for solutions inside the unit cell. And outside the unit cell, they must be periodic if I look for solutions in terms of u. Then, of course, once I determine u, I can construct psi easily, the solutions throughout the space. So Bloch's theorem is, in some sense, that's actually the spirit, the usefulness of Bloch's theorem is that it allows me to restrict the search for my solutions from the whole space into the space of periodic functions, that is, functions where that if I define them within a unit cell are defined also anywhere else in space. But what is the equation that determines u now? We know the equation that determines psi. It's an eigenvalue equation. But what is the equation that determines u? I've simplified my job because I'm now looking for periodic functions, but I also need to write down an equation, a differential equation that determines u. Well, the obvious way to do it is to just take this object here and put it here and see what we get, right, in terms of the equation. So let's do that. Plus v u k e to the I k dot r equals to e u k e to the I k r. And of course, the challenge here is to notice that this is a delta squared. The v part is just a multiplicative term, so it doesn't really do any harm. The problem here is that this is delta square, and delta square now applies to a product of functions. So, does anybody remember what is the result of taking delta square applied to a product of two functions? Well, let's do it. So delta square means delta cross delta, cross dot gradient, right? That's the meaning of delta square. But the gradient, I can take the gradient of the two functions separately, right? I can do f gradient of g plus plus gradient of f times g. Then I have to take the gradient again. Well, let me continue. So this will be gradient of f dot gradient of g plus f gradient squared delta square of g plus gradient square of f times g plus delta f dot delta G, right? Just have to remember the definition of delta square. Delta square is the gradient of, well, it's delta dot gradient of f times G. And now I can, of course, collect these two terms here, and I get something which probably sounds obvious at this point, plus twice delta f delta G plus G delta square f. Okay? I need to know that because I need to take now the gradient of this thing here. I will also need to know the gradient and the delta square of a plane wave. Are you familiar with this? Can you tell me right away what is the gradient of a plane wave? I, k, this is the gradient only. Gradient, okay, so I k e to the I k dot r. If you're not familiar with this statement, just do the calculation. I mean, just express it in terms of Cartesian coordinates and you'll find it out. So therefore, if you take delta squared, this is minus k squared, right? I'm sure you know this, right? Because otherwise you wouldn't know anything about quantum mechanics of free particles. Okay, so with all this in mind, let me work out this. So minus h squared over 2m. All right, now I have delta square applied to this product. The first term is uk times delta squared of e to the I k r. So this is minus k squared e to I k dot r. Then plus 2 gradient of u, k. Let me remark, if it wasn't clear, that this gradient is a gradient as a function of real space. Okay, so it's not a gradient with respect to k. It's a gradient with respect to whatever is the argument of this function, which is the real space. Just again, not to confuse the two spaces. Times the gradient of the plane wave, which is I k e to the I k dot r. All right. Last term, it's delta squared uk e to the I k dot r. And we are done with the most difficult part. The rest is trivial. The rest is just v uk e to the I k dot r equals to e uk e to the I k dot r. All right? So that was the only difficult part, was really carrying out the delta square here. Okay, so let me now remove everywhere e to the I k dot r, which is present everywhere. And let me regroup delta squared. I can invert here the order. I mean, this is not operators any longer, so it's plus 2i k. K now is just a number, right? So I can exchange it with the gradient. Delta minus k squared applied to u, okay, plus v u of k equals to e u of k. All right? What's the difference between this equation here and the original Schrödinger equation that we had, this one here? Well, first of all, it's an equation that applies to u, not to psi any longer, which is good for us because we know that u is simple to handle because it's a periodic function. On the other hand, the price we pay is that we are introducing two additional terms here, which were not there at the beginning. So it's no longer just kinetic energy plus V, but it's something else. There's a kinetic energy, there's a term proportional to gradient, so it's like a momentum, sort of a magnetic field, if it wasn't for the fact that this is the scalar product. This is just a constant, right? K is a number, is a vector, so this is just a constant, a number. So this is not really harmful. This is a bit more harmful because we are introducing an additional term in the Hamiltonian which is proportional to the gradient, that is to the momentum operator. In fact, I shouldn't really call this an Hamiltonian because this is not an Hamiltonian. U is not a wave function. It's only part of the wave function. It's the periodic part of the wave function. So you always have to think of this as just a mathematical exercise, not really as a transformation into a new Hamiltonian. The real Hamiltonian is H. We're expressing psi in this, decomposing psi in this form, and for one part of the wave function we obtain this second-order differential equation. There's not more than we can say about it. It's not a real Hamiltonian. We can, of course, think of analogies if we want to solve this second-order differential equation, but we shouldn't really call it an Hamiltonian because this is not a physical Hamiltonian. U is not a wave function. It's only part of the wave function. So the price we pay in order to be able to introduce a periodic function is that, unfortunately, there are some additional terms in the Hamiltonian. I will call it Hamiltonian anyway, and I will actually give it a name. So I will actually write this as h of k, u k, okay? By h of k, I mean gradient plus this plus v, of course, everything. And I give it this name, h of k. So I call it Hamiltonian, but you have to keep in mind that this is not a Hamiltonian. The real Hamiltonian is only this one. It's a second-order differential equation. If we're able to solve it, we get u, and therefore we are able to solve our original problem. But the advantage now is that this second-order differential equation applies only to periodic function. So this problem is defined only in the space of periodic functions. That is, we can restrict our search to periodic use. So that's our goal now. Instead of solving this equation, we're now going to try and solve this equation in the space of periodic functions. So let me summarize everything here. So h of k is minus h squared 2m delta square plus 2ik dot delta minus k squared plus v. And the problem we are solving is h of k, u of k equals to e of k, u of k. So that's the new problem that we are solving now, which just follows from Bloch's theorem. the way, so far, no approximations. Everything is exact. We haven't really applied any approximation of any kind. Of course, as long as we believe in Bloch's theorem. All right. So K belongs to the Brillouin zone. Oh, sorry, I forgot to mention. K belongs to the Brillouin zone, and the possible values of K's are infinitely many. So it is true that we have restricted our search to the set of periodic functions. But not only we have complicated our life because we have introduced these two additional terms in the Hamiltonian, we're also complicating our life because now we have to solve this problem for all possible values of K in the Brillouin zone. Okay? Not just for one. Okay? Because K belongs, it's a generic vector that belongs to the Brillouin zone. If we want to know the full spectrum of solutions, we cannot restrict ourselves to a single quantum number. We have to determine the solutions for all Ks. So we need to solve this problem, slightly more complex than the original Hamiltonian, and we have to do it for all possible Ks in the Brillouin zone. All right? And notice that the Hamiltonian here, I call it Hamiltonian, but it's not a Hamiltonian. This second-order differential equation changes if I change K. Changes because of a trivial offset. That's not really important. But more importantly, it changes because this K here, this parameter K, changes the strength of this term here, this gradient term. So every time I change K, I change Hamiltonian, change solutions. So I need to recalculate the solutions again. So I need to calculate the solutions of this problem for all K's in the Brillouin zone. And each K will correspond to a different Hamiltonian. In other terms, HK is a second-order differential equation that depends parametrically on K. There is a parameter that controls the second-order differential equation, the Hamiltonian. And I vary K, the Hamiltonian changes, I get different solutions. And I have to do it for all K's in the Brillouin zone. Okay. Now, what's happening? Let me now try to imagine. I'm not going to solve it. I'm trying to imagine what the solutions of this problem could be, to visualize the solutions of this problem. So let me now report along the y-axis the possible energies, and along the x-axis the possible values of K. Now, I know we're in 3 dimensions, but allow me to use a single axis to represent the 3-dimensional space. Or if you wish, you can think of a 1-dimensional problem. Therefore, K is only a single line. So there will be somewhere there will be the end of the Brillouin zone, here and here. If it's a 1-dimensional problem, this is pi over a and this is minus pi over a. Okay, so solutions will only be defined within some boundaries, right? This is outside the Brillouin zone, so we don't really need to go outside. We just stick to vectors K within the Brillouin zone. And let me fix a value of K, an arbitrary one, this one. I fix the value of K. I go back to my Hamiltonian. The Hamiltonian takes a specific form because K is fixed, is given. I solve it. Now, here there is an important statement that I have to make. If I solve an Hamiltonian and I look for solutions which are periodic, the Hamiltonian will have, at least for the lowest level, a discrete spectrum. Okay? Mathematically it's not straightforward to prove, but think of it, for example, at just the free electron problem. You have a free electron problem that you want to solve, and you force the solutions to have a given periodicity. Okay? If you force the solutions to have a given periodicity, you can only have the solutions plane waves which are commensurate with the period. One time the period, 2 times the period, 3 times the period, right? Only wavelengths which are commensurate with that particular periodicity will be allowed. Okay? That, of course, leads to a quantization of the spectrum, of the energy spectrum, leads to a discretization of the energy spectrum. Right? So I'm just going to argue this in very qualitative terms. If you have the free electron problem, solutions are of the form plane wave form. If you force these solutions to be periodic with some periodicity, well, let's do it in one dimension. If you force them to be periodic with periodicity A, right, only values of Q equals to 2 pi over n A, 2 pi n over A are periodic with periodicity A, right? And therefore, even the energies, the energies will be 2 pi n over A squared, right? So they will be discrete. Only for specific integers you will have energies. There's an equivalent statement if you, instead of working with periodic systems, you work with confined systems. If you confine your solutions of a quantum problem into a well-defined finite region, the spectrum is discrete. So these are all general statements that you can make in quantum mechanics. I don't want to prove these statements, just want you to have a general feeling that this is not so far from the truth. Okay? So what I'm going to use now in my discussion is the fact that once I restrict the solutions to this Hamiltonian to periodic functions, for a given k, I'm going to obtain a discrete spectrum of solutions. That's the only ingredient that I need at this point. So for a given k, well, if it's a plane wave, if it's a free electron problem, the spectrum will be given by n squared. This is not a free electron problem because I have a potential V, a generic potential V. So, well, I will have some solutions. I will have, say, a solution 0, which I can label by 0. Actually, let me label it with 1. That's the first one. I will have another one here, 2, perhaps another one here, 3, another one here, 4, and so on and so forth. I mean, I will have a spectrum of solutions, which will depend, of course, on the potential V for a given k. The only additional information I've introduced, in addition to these statements, to this theory that we've developed so far, is that I'm arguing that the spectrum of this Hamiltonian is a discrete spectrum, generic discrete spectrum. So I'm just labeling the states with 1, 2, 3, 4, and of course 5, 6, 7. I mean, it's an infinite number of states, which are the eigenvalues of this Hamiltonian, the solutions of this problem, for a given k. Fine. Are you all fine with this? Yes? No? Yes. Let me change now k and take a k which is very close to the previous one, but to the left. Okay? I'm now moving just a little bit to the left. How is the Hamiltonian going to change if I change k? If I change k, it's going to change a little bit, but it's going to change in a continuous fashion, right? Because if I change k, this here the Hamiltonian will change just a little bit. I mean, continuously change as a function of k. This is, after all, a continuous function of k. So obviously, also the eigenvalues will change only continuously with respect to the ones that I obtained at the given k, at the previous one. So, well, I will have, again, a discrete set, but the set will correspond to values which are continuously connected to the previous one, right? After all, the Hamiltonian is a continuous function of k. So the eigenvalues themselves will change smoothly if I change k. In fact, I can continue this exercise for all k's. And, well, I will get some lines here. Right? Each one of these points will be the solution of h of k for that particular k. And the reason why these are lines and not just random points is because the Hamiltonian that generates those solutions is an Hamiltonian which is continuous on k as a function of k. So what we've concluded out of these arguments is that if I express the solutions of my problem in terms of k, this quantum number k, I'm going to get some lines if I'm in one dimensions. Of course, if you now expand k into a three-dimensional space, these are no longer lines, but they are three-dimensional surfaces. If this is two-dimensional, this will be two-dimensional surfaces, of course. And in 3 dimensions, this will be three-dimensional surfaces, with E being the fourth dimension, of course. It takes a while to visualize something in 4 dimensions, but so that's why we just do it in 1 dimension. In 1 dimension, these are just lines. Now, what I've shown here is what goes under the name of band structure. And these ones are the bands. Or to be more precise, these are the electron bands. So the solutions of the electronic problem in a periodic system. Now, as a consequence of this derivation, we now know that we can classify all the possible states that solve our Hamiltonian actually with 2 quantum numbers. One is the quantum number k, the one we've already talked about, and the other one is the quantum number that defines which solution I select out of the discrete spectrum generated for a given k. So one of the consequences of this discussion now is that there are the psi, I'll write it here. I can actually express it using 2 quantum numbers, k, the obvious one, but also an n, an integer, that labels which band I'm referring to. So in other words, the general solution to my problem can be expressed in terms of a periodic function times a phase, and this periodic function can be labeled according to the quantum number k, which belongs to the Brillouin zone, plus an additional quantum number, which for every k tells me which band I'm considering. That is, any solution of this periodic Hamiltonian, I can use 2 quantum numbers to define it. A continuous one, k, which spans throughout the Brillouin zone, and a discrete one, n, which labels which band I'm referring to for a given k. So there are 2 quantum numbers that define solutions of a periodic Hamiltonian. The band index and the k vector. If I give you these 2 indices, you can tell me exactly which solution I had in mind. Just like if I tell you what is the principal quantum number and what is L and what is M, you can tell me what is the eigenstate of the hydrogen atom problem that I'm referring to. Yes?
I have a question. Do we have an infinite spectrum here?
Yes. We do have an infinite spectrum because, well, this is, it's not a Hamiltonian, but it's a second order differential equation whose mathematical properties are those of a Hamiltonian. Okay? And we haven't proved it, but you can actually prove that if you search for solutions of the second order differential equation, Hamiltonian equation, in the space of periodic functions, the solutions are going to be discrete, but of course there's going to be an infinite number of them, because an Hamiltonian always the solutions of an Hamiltonian are always an infinite, it's a Hilbert space, right? So it's defined, so you will get an infinite number of solutions. Yes, of course. So the question is there a possibility to have degenerate states? Yes, of course. This drawing here was based on the fact that these bands never intersect. But you may have intersection of bands, right? You may have these lines may actually intersect. You may have a situation in which this goes up and this goes down. So there will be an intersection. Here, it's a degeneracy, for example. You may also have degeneracy more likely at the edges or at the center of the Brillouin zone. So there may be degeneracies, yes. The reason why there may be, it's more likely to have degeneracies here than elsewhere is because if you look at this Hamiltonian, if k is equal to 0, the Hamiltonian is the Hamiltonian of the potential V. So if the potential V has certain symmetry properties, which it may have, I mean, suppose you are in a closed packed system, for example, in an FCC system, then V certainly has a number of symmetries. If you rotate V, it remains the same with some discrete rotations. So these kind of symmetries typically reflect in degeneracies. So at k equals to 0, you may have plenty of degeneracies. As soon as you go outside k equals to 0, you're introducing a term, this one in particular, this is irrelevant, but this one in particular, that breaks all the symmetries. Because as soon as you introduce, if k is an arbitrary number, there's no longer any reason why there should be symmetries remaining in the system. Well, there are in some cases, but not necessarily. So you typically rarely see degeneracies outside the center of the Brillouin zone, with some exceptions, of course. So yes, there may be crossings, there may be degeneracies, there may be a number of things. This plot was just the oversimplified, one possible scheme. In fact, there are a number of mistakes there that you'll become more familiar later on. Well, actually, let me discuss one obvious mistake that descends directly from here. Right, let me discuss it here. What happens if I take k and I send it to minus k? Suppose I solve the problem of k. Can I say something about the problem at minus k? That's the question. Well, let's see how the Hamiltonian changes if I go from k to minus k. H of minus k is minus h squared over 2m delta square minus 2i delta k. All the rest remains exactly the same. Right? So here is the only change, this minus here. That's the only difference. So obviously, h of minus k is equal to h star of k. Right? The complex conjugate. What I did is only to change the only term that contains I here. Okay. But if I know the solution, sorry, you. I know that this is true because I assume that I solved the problem at k. Let me take the complex conjugate of this equation. Well, E is a real number. This is h of minus k, right? So U star is an eigenfunction of h of minus k, right? According to this equation, U star is an eigenfunction of h of minus k, with eigenvalue h of k. All right? So if I send k into minus k, the solutions will be identical to the solutions at k, the only difference being that U's will be complex conjugates of the U's at k. The energy will be exactly the same. And of course, when I construct the real solution, which is psi, I will have U star here, but also E will change sign, right? The exponential part will change sign because I change k into minus k. So the whole thing will become the complex conjugate of what it was at k. That's it, as simple as that. So knowing the solution at k gives me in a trivial way also all the solutions at minus k. The only thing I have to change is to take the wave functions and take the complex conjugate. The energy remains the same. Okay? So that means that this plot is clearly wrong, because this plot here there should be mirror symmetry around k equals to 0, right? Because whatever I get at k, I must get it at minus k. So, well, in fact, I try to maintain some symmetry here, even it's not so nice. Here there is a little bit, well, it's not certainly symmetric. So there is clearly a mistake in this plot due to the fact that the energy as a function of k has a symmetry, E of k equals to E minus k. Okay, so there is a mirror symmetry, not a mirror symmetry, sorry, it's mirror symmetry in one dimension. It's a reflection symmetry. I mean, it's a k minus k. Inversion symmetry in 3 dimensions. All right, so E of k, E of n, let me put an index n, because this is now, there are different energies for every band, is equal to E of n minus k. Another interesting property is that, of course, because of all what we discussed, before, obviously, E of k plus g, I suppose I move away from k to by a reciprocal lattice vector. Remember that by capital G I labeled the reciprocal lattice vectors. Because of all I said before, this must be equal to E of k, right? That these solutions are periodic in reciprocal space, not in real space, but in reciprocal space. That is, if I find a solution at a given k, the solutions at k plus g will be identical. Okay? So therefore, energies will also be identical if I move away by a reciprocal lattice vector. Of course, if I do that, I'm going out of the Brillouin zone, obviously. Right? If I add to a Brillouin zone vector a g vector which is not trivially 0, I'm going outside the Brillouin zone. But the reason I mention this is because this has some consequence, some practical consequences. Suppose there is no degeneracy. Okay, so suppose that this band here is just there on its own. Okay, no crossing with other bands. Now, if I go outside, the function must be periodic. So it must continue like this. But wait a sec, this is not accepted, right? Because there's no reason why there should be discontinuities in the solution. The solutions are eigenvalues of a continuous kind of equation. So this thing is not acceptable. So here, in order for this to be periodic, I have to have a zero derivative here in order to be able to establish periodicity. Okay, as well as here, of course. Otherwise, it's not going to be periodic. The only way I can match the function here and there. Oh, notice, okay, sorry, I'm using two statements here. I'm using the fact that it is periodic, and I'm also using the reflection symmetry. Because otherwise I could have written this like this, and this like this, right? But this wouldn't be consistent with the k minus k symmetry, because here it would go down and here it would go up. So the combination of translational symmetry in reciprocal space and k minus k symmetry forces me to have a flat derivative at the edges when I get to the edges of the Brillouin zone. If I don't have any degeneracy, of course. Okay, I'm just listing a number of consequences of all these symmetry properties. So this is an interesting one, although this is not in principle interesting because you're going outside the Brillouin zone. It allows you to make statements about the way the bands have to reach the edge of the Brillouin zone. They must reach it, if they are non-degenerate, they must reach it in a flat way. So there are a number of consequences again. Symmetry, k minus k, periodicity, and I would say that's it for the time being. Okay. Let me now discuss another important fact, or number of facts. And this is all related to the way we fill the bands. Do you have any question? No? Oh, okay. Are you tired? Yes. A little bit. Let me just finish this and then we'll finish, okay? Let me discuss now filling of bands. How do I fill them? With electrons, of course. Now, I have my Hamiltonian. I didn't specify anywhere how many electrons I had in my system. So I need to, at some point, after I gave you the Hamiltonian, I need to tell you, well, this Hamiltonian is, given by this potential, but I also need to tell you how many electrons I have in my system, right? So, in particular, I need to tell you how many electrons I have, the number of electrons in the unit cell. Notice that I'm not making any reference now to how many atoms I have in the unit cell, where are the atoms, details that we had to discuss when we were using a specific model, the hydrogen atom chain, for example. Here I'm talking about very general statements that don't really depend on the actual number of atoms, where the atoms are located and things like that. The only thing I'm assuming is that the potential is periodic. So if I go from one unit cell to another unit cell, the potential is exactly the same. That is, the atoms are placed in exactly the same positions. And this is all I need in order to make these statements. I need something else, however, in order to fill the bands, and this is the number of electrons I have in the whole unit cell. I don't need to know the number of electrons that are of one atom, of another atom. I need to know the total number of electrons that I have available, because at the end of the day, well, of course, in order to calculate this number of electrons, I will use the number of atoms and the kind of atoms that I have in the unit cell. But I don't need to say that these electrons will stay on top of a given atom or stay on top of another atom. At the end of the day, I have a spectrum, I have a total number of electrons, and I will have to fill this spectrum according to the total number of electrons. It's like the covalent bond, or like this one-dimensional problem. We don't need to know where the electrons came from, but we need to know how many we have, because we need to be able to fill this band structure properly. So this is a parameter that is somehow outside our theory so far, but needs to be specified at some point in order for us to be able to fill properly the bands. Now, how do I fill the bands? The basic principle I have to keep in mind when I fill bands is that each band corresponds to a number of states equals to 2 electrons per unit cell. But 2 per unit cell. Or sorry, I shouldn't say it this way. It's the number of states depends whether do we want to assume. Let me put specifically 2 electrons, okay? Because the number of states is 1 state per unit cell, but I can place in each state 2 electrons, okay? So what I want you to remember is that each band corresponds to, if I fill it completely, I will need to use 2 electrons per unit cell, and that fills completely a band. Okay. Now we didn't prove it. Well, we proved it for a one-dimensional case. We didn't prove it for the general three-dimensional case. It can be proved. We don't want to do all the mathematics, but this is an exact statement. Okay, so you have to keep it as not as an approximation. This is actually part of all our series of exact statements that we've made so far. Each band corresponds to 2 electrons per unit cell. So suppose the band structure is this one, and I have 1 electron per unit cell. So I'm dealing, for example, with, let me make specific examples, okay, concrete examples. The first example we make is, for example, we are working with lithium. Actually, no, with, oh, yes, let's do lithium. Lithium, which is a BCC crystal, right? The crystal structure of lithium is BCC, at ambient conditions at least. I hope so. Yes, I think so. So, BCC is a Bravais lattice, okay? There's 1 atom in the unit cell, 1 lithium atom in every unit cell. How many electrons do I have? Right? Lithium has 3 electrons. One of them, well, lithium is 1s2, 2s1, right? Now, the 1s state is very deep in energy. So we can actually forget about the 1s state. It's going to lie down, several meters, downward here. And it's going to be completely filled because we have 2 electrons there. It's a core state. We don't need to bother about that 1s state. Well, it's interesting to know that it will give rise to a band somewhere deep, in this plot, but there are 2 electrons there in this state per unit cell, because there is 1 lithium atom per unit cell, so there are 2 electrons per unit cell. So this band is going to be completely filled. And it's very deep, filled and deep. So we can forget about it. More interesting is the 2s state. The 2s state will correspond presumably, or will give rise presumably, to the first band in our spectrum. You can, with some imagination, think that the next one could be the 2p, and then the 3s, and so on and so forth. That's not completely true, because at some point the bands will actually mix up. So the atomic character of the wave functions is actually lost. But you may, if you want to keep some understanding in terms of atomic physics, you can think of this state to originate at least from the 2s state of lithium. Whatever it is, it's the first available band after the deep 1s band. And you essentially have 1 electron here per cell. Again, 1 atom per cell, so 1 electron per cell. Now, this full band corresponds to 2 electrons per unit cell, so we will have to fill the band, half of it, like we did, you remember, for the The green states will be filled. The white states will be empty. Not only these ones, but also this ones, this one, this ones, and so on and so forth. And we need to do that because we only have 1 electron per cell. So we cannot fill the whole band, which is 2 electrons per cell. We need to fill it by half. So we need to stop at some point. And we use the principle that we first fill the lowest available states. Now, this particular value of the energy, where the filled states stop, it's called the Fermi energy. So the Fermi energy is the energy of the highest occupied state in my band structure. In molecular physics, it would be called HOMO, the highest occupied molecular orbital. In solid-state physics, we call it Fermi energy. It's the energy of the highest occupied state. Yes? Not really. We will see. We will study all this in the context of the free electron gas later on. Okay? But not necessarily. I mean, it's all part of the same theory, but it's not really strictly speaking related to the Fermi gas. It was Fermi who actually introduced all these concepts. Not just him, but he gave a number of important contributions to the whole theory. So it's not really related to Fermi gas, although, of course, they are connected in some way. But you'll see it later on when we discuss the free electron gas. So this is called Fermi energy, right? The highest occupied energy of the system. What if we are dealing, instead of lithium, we are dealing with magnesium? Magnesium crystallizes in HCP, BCC. But let's say BCC again, okay, just to keep the discussion simple. Assume that magnesium crystallizes in BCC. All right, magnesium, how many electrons? 12, right? It's, okay, magnesium is 1s2, 2s2, 2p6, 3s2. So 12, correct. Right. Now, this block of electrons is, once again, very, very deep down. These are the core states that we discussed at the beginning of our classes. We're not interested in that. These are going to be deep states. They are all full, completely filled, right? Actually, they're even numbers. So whatever bands we have, because we have an even number of electrons, they're going to be completely filled. And what we're left with is this 3s2, and that's really what is of interest for us. 3s2 means that we have 2 electrons per mg, 2. If there's 1 mg per unit cell in the BCC crystal, that means we have 2 electrons per cell to place. And if we assume that this is the band structure, notice this does not necessarily need to be the same band structure, because if I now work with magnesium, the potential felt by the electrons V is going to be different. If anything, because the Coulomb attraction now corresponds to 2 plus, not to 1 plus like for lithium. Okay? So the potential is different. This band structure, which is the solution of the problem with the given V, is going to be different. So it's not necessarily the same. Let's assume that it is exactly the same. I don't want to derive it now. But let's assume it is the same. We have now 2 electrons per unit cell. We can now fill completely the first band with magnesium, right? So with magnesium, we can now go all the way up to the top. Here. And that's it. Where is the Fermi energy here? Well, the Fermi energy is probably somewhere here, right? The top of the band. That's the last available state that we have occupied. But now there is something remarkable with respect to before. Before, the last available electron here, with the one with the highest energy, was arbitrarily close, actually was essentially coinciding with the first available state, empty state. Okay? So if I were, for example, thinking of excitations in my system, in the previous case with lithium, the excitation energy, the minimum excitation energy, would be 0 in lithium. Because I have an electron here at the Fermi energy, I can place it in the first available state above the Fermi energy. That's empty. Right? So the excitation energy for that particular configuration, the green one, was 0. If I now do the same for magnesium, I feel completely disbanded. So there's no available state any longer that I can excite my electrons into. The first possible state is, well, it must be the same, by the way, because of periodicity. So it's either this one or this one, which must be the same because the periodicity of the solutions implies that solutions here must be identical to solutions here. All right? So there is a finite energy that I'm required to give to the electron in order for this electron to be excited. Well, any one of these electrons requires a finite energy in order to be excited. So the first excitation has a finite energy. That's going to affect dramatically the properties of my system. And we'll see the consequences in quite some detail later on, in terms of transport, in terms of optical properties, in terms of a number of consequences. What I want you now to realize is that there is a clear qualitative difference between the green situation and the orange situation. The green situation, there was clearly no excitation energy. There was freedom for the electrons to be excited into empty states immediately available at 0, in principle 0 cost. For the orange situation, I need to overcome a gap. Let me start using terms that... so this is a gap, or an energy gap, if you wish, in order for electrons to be excited into the first available state. Yes?
Do we have the same gap structure if we have degeneracy in our system?
Okay, the question is whether you have the same gap structure if you have degeneracies. The answer, of course, is no. This discussion was based on a particular choice of the band structure. I will now give you a number of different, qualitatively different band structures, and we will discuss all these examples now in a moment. But the answer to your question is no. If you have degeneracies, of course, we need to examine case by case. I'm just giving you some situations now, and I'm going to discuss the... yes?
I have some questions. Is Fermi energy negative or positive?
Well, it doesn't really matter, I mean, because the zero of the energy can be wherever you want here. If you wish, we can discuss where to place the zero of the energy, but that will take me a while. The zero of the energy in an infinite system is not mathematically defined, unfortunately. So you need to have a surface, and you need to tell me where the vacuum level is if you want to put the zero of the energies here. Otherwise, it's not defined. After all, we don't need to define it because energies are all defined within an arbitrary additive constant, right? So we don't need to know where is the zero. If you wish to actually put a reference, the best reference is the vacuum level. But in order to have a reference, to have the vacuum level as a reference, you need to have a finite system. So your crystal has to be finite because you have to go throughout the surface and reach the vacuum level. For an infinite system, there is no vacuum level because vacuum is nowhere. Sorry, let me finish this. Yes.
Also, I want to know,
What is N?
The 2 electrons, okay, the 2 last electrons are.
Yes, so the last 2 electrons are in the 3s state.
But when I saw the gap should be between.
So if you want to continue thinking in terms of atomic physics, this could be the 3s state and this could be the 3p state. But it's not really the case. It's not like this. They're closely related. They're relatives of the atomic orbitals, but they're not exactly the atomic orbitals. It's the solution of the problem of this periodic problem. Yes?
Okay, is the Fermi energy the same for elements of the same kind,
I give you as an answer the same answer I gave to him, namely, the absolute position of the Fermi energy has no meaning unless you give me a reference. Okay? And choosing a reference is not trivial. The most obvious reference is the vacuum level. But the vacuum level requires me to introduce a surface, and so a number of complexities that I haven't introduced here. There's another reference which some people use, and we will use in the future, which is the bottom, the minimum available state. Okay, so you may wish to measure the Fermi energy starting from the bottom of your bands. Okay, but the bottom of your bands itself may depend from on the system you are. Yet, you may wish to say, okay, let me define Fermi energy starting from the bottom. Whichever system I consider, I start from the bottom and measure the Fermi energy from the bottom. If you do it that way, we can actually say something about the value of the Fermi energy. We'll do it in a couple of lectures when we discuss the free electron problem. Okay? Yes?
Can an electron jump or move to the next brilliant zone before it excites to the next higher state?
You want electron to jump from here to another Brillouin zone? Huh? Okay. All right. So let me assume that I take an electron from here and I bring it to the next Brillouin zone. What is the meaning of that? The meaning is that I'm going to fill a state which is identical to a state here because of periodicity, right? Any state that I find here is identical to a state that I find inside the Brillouin zone. But that state was filled. So there's no way I can place an electron and put it somewhere else. Because putting it somewhere else means putting the electron somewhere within the Brillouin zone, and that's not allowed if the band is filled. So the only possible excitation for an electron here is to go up. In the orange case. Notice I'm not exhausting the possible number of cases. I'm just giving you a couple of examples, right? I'm going to give you more examples now. In fact, those of you who are already familiar with solid-state physics might wonder, how can magnesium have an energy gap, an excitation energy gap of excitation? Those of you who are familiar with solid-state physics, and we'll come back to that, probably know that a metal is characterized by a vanishing excitation energy, all right? By the green sort of configuration, not certainly by the orange one. Yet, magnesium is a metal. Bulk magnesium is a metal. So what's happening here? In this schematic band structure, we find magnesium to be an insulator. That is a system in which there is a finite excitation gap okay, so there's something wrong here. Let me give you another example, and that what we thought could be wrong is actually not so wrong. So I gave you the example of magnesium, but magnesium doesn't really behave this way. Otherwise, it would be an insulator, and it's not. Suppose I have this band structure and others here. Well, of course, with k minus k. I'm drawing very qualitative pictures here. It's not really. E. Let me now repeat the magnesium argument again. I have 2 electrons. Good. I have to start use the orange, I guess. Okay. I will start filling the initial state here. By the time I get to this point, if I did everything properly, I've probably used half of my available electrons, that is 1, right, if by the time I get here. But as soon as I go past this point, suppose I get here, well, this state becomes available. So I'm not allowed to really go all the way up to this point. Because then if I went up to this point, filling the states up to this point, I would neglect the fact that here I have states which are empty and are available and are lower energy. So obviously, what I should do is to go up, start filling also these states here. And presumably, I mean qualitatively at least, I will have to stop presumably here. So this remains white. And I will have to fill these states here. So this one, and this one. And the Fermi energy will be here. And I use 2 electrons per unit cell, right? I fill completely, well, I didn't fill completely a band, but I filled almost completely a band, and what was left, I used it to fill the remaining part of the other band. But if I do my counting properly, I'm done. That's the way I should do it. So magnesium is a metal, right? Because I have a 0 excitation energy now. The highest available state is here, and there are arbitrarily close excited states on which I can excite. So you see, I just changed slightly the topology of the band structure, and I immediately turn an insulator into a metal. Right? Now, I will be consistently using this terminology, although it's not fully correct. I think I can move this side of the blackboard. I will consistently from now on use the terminology that an insulator for me is something with finite energy, excitation energy. So different from 0. Okay, and a metal is when the excitation energy, the minimum excitation energy is equal to 0. This is the way I will define my systems. There is, of course, a word of caution here. There are systems, real system, materials, for which the minimum excitation energy is 0 that don't behave like metals. So the phenomenology is actually a bit different. There are some exceptions, I mean a few, but there are exceptions. Let's stick to this definition because it's simpler for our purposes. But I would like you to keep in mind that what we define as an insulator, what we define as a metal, is just this for our purposes. The truth is that there are some systems, rare classes of category of systems in which the minimum excitation energy is 0, and they don't behave like metals. They don't conduct electricity. But let me keep using this notation because this definitions, this terminology for simplicity. Okay. Let me make a couple of final statements about this. Suppose I have an odd number of electrons per unit cell, of course. 1, 3, 5, 7, 9. What can I say about whether the system is a metal or an insulator? I have an odd number. If I have an odd number, there's no way I can fill completely a given number of bands. I will have to leave at least one half-filled, right, if it's odd. Because if I were able to fill completely a given number of bands and that's it, that would correspond to an even number of electrons. So if it's odd, it must be either like this, I mean, and then there is an extra electron somewhere else, or the last available band is divided in two. So that is, the Fermi level cuts the last band, because that band must contain one electron, not, I mean, the final one. Okay? So if I have an odd number of electrons, this is never true, right? Because if this is true, then I have to be able to fill completely a given number of bands, but that corresponds to an even number of electrons. Okay? So an odd number of electrons per unit cell, not an insulator. Well, it's a metal. Okay? Yep.
If we consider, for instance, sodium. Okay.
Sodium, yes. If you
11 electrons, right?
right.
And now when we write the configuration, we will have one is, okay, let's write.
We'll have an extra, we'll have 1s2, 2s2, 2p6, 3s, no, sodium is actually 11, okay. So it's, 3s1, right?
Yeah, but there is cases, okay, the outermost will be, okay, half filled and full filled, right? So it becomes raised to, and the 2p will be, instead of p6, it becomes 2p5. And it is more safe.
What you want to have is that 3s, okay. All right, so you're arguing that sodium is 1s2, 2s2, 2p6, 3s1. Okay? Then you want to say, okay, I think I know what you mean. You want to take an electron from p, make it 5, and do 3s2.
And there are cases in which case it is stable, right?
Okay, then this is completely filled. And what about this one?
Yeah, it's not completely filled, but there are cases in which it is stable, right?
It is stable only if this half-filled band is above the 3s2. Otherwise, this electron will fall down here. So what you're saying may be true, but if, in order to be true, that the band that contains these 5 electrons, or one of them at least, must be above the 3s2 band. Otherwise, it would be more convenient for the electron to fall down and fill the available space.
Yeah.
You're talking about an excited state, but we're not talking about excited states here. We're talking about the ground state of a system.
Yeah, okay. Yeah. Yeah, it looks natural to have 2p6 and 3s1, but...
No, but what I'm arguing is that, I'm not arguing that it is not possible that this happens. But if it does happen, then that 2p state must go above the 3s2. And then you will still be left with an empty, a partially empty band, because the 2p5, the 5 electrons, they will have to be placed in 2 plus 1/2, right? So whatever you do, I'm not saying it cannot happen. What I'm saying that if it does happen, in any case, you end up with this statement. There's no way you can violate this statement, because in order for the system to be an insulator, you must fill completely all the bands, and that leads to an even number of electrons. Okay? Now, one has to be careful, however, and that's something, of course, this is the number of electrons per unit cell, and therefore I can say that sodium is a metal, but only if there is one sodium per unit cell. If the unit cell of sodium was made of 2 sodium atoms, by chance, because, I don't know, HCP, for example, which contains 2 atoms per unit cell, then I wouldn't be able to say that sodium is a metal, because there would be 2 atoms per unit cell, and therefore the number of electrons, total number of electrons, would be again even, because the sum of 2 odd numbers is an even number. So be careful, it's per unit cell, not per atom, of course. Okay? Fortunately, the unit cell of sodium is a monatomic unit cell, it's the Bravais lattice, so I can actually make this statement. Sodium is a metal. lithium is a metal. What if I have an even number of electrons per unit cell? What can I say? Can I say that the system is an insulator? Here's the counterexample. I have an even number of electrons. Well, if the band's crossing this way, it remains a metal. I certainly cannot say that the system must be an insulator. Yes?
If we don't have the degeneracy between bands,
Mm-hmm.
so
No, okay. I need to give you another example then. You seem to like this degeneracy, but this is not really. No. I'll give you another example where there's no degeneracy, and this is this one. Wait a sec. Yes. Okay. There's no degeneracy here. Still, the Fermi level will be somewhere in between. And I will have to fill a little bit of this and a little bit of this. Okay, no degeneracy. So you're not required to have degeneracies too. So, even number of electrons, what can I say? Nothing, right? It can be a metal here, or it can be an insulator. But if I say that the system is an insulator, that is finitization different from 0, what can I say about the number of electrons? Must be even, right? Because in order to be an insulator, I must be able to fill completely all the bands below and leave all the bands above empty. So it's the opposite, the arrow, that holds. If it is an insulator, the number of electrons must be even. Okay? So be careful about the arrows here. If it's a metal, it doesn't need to be odd number of electrons. It can be even. However, if it's odd, it must be a metal. If it's even, doesn't need to be an insulator. But if it's an insulator, must be an even number of electrons per unit cell. Okay? Yes?
I'm confused how you have explained between the number of atoms and electrons.
Okay, yes. So your question is about number of atoms and number of electrons per unit cell. All what I'm saying holds if I count the number of electrons per unit cell in my crystal. So when I make considerations based on the number of electrons for given atoms, here, for example, I'm assuming that there is one magnesium atom in the unit cell. That is, that the crystal structure of magnesium is a monatomic crystal structure. In that case, I can say, well, there will be 2 electrons in the unit cell. Same here in lithium. There will be 1 electron in the unit cell. However, suppose that magnesium crystallizes in the HCP crystal structure. HCP contains 2 atoms in a unit cell, right? So the number of electrons in the case of lithium, if lithium crystallized in the HCP, the number of electrons in the unit cell for lithium, let me forget about the core states, will be 1 plus 1, 2. Okay? So I would be in a situation with an even number of electrons per unit cell if lithium was crystallizing in HCP. Okay? So what I could say is essentially nothing. It could be an insulator, it could be a metal. If it crystallizes in the FCC or BCC, then I can say it's a metal, for sure. I'm pretty sure that lithium, if I were able to place lithium in an HCP, it would be still a metal. But I cannot say it from my general considerations. While I can certainly say it for sure if I know that lithium is in a monatomic structure, that it is going to be a metal. Yes?
If we have an atom with many electrons in the valence state,
Yes?
then can we argue the same thing here? Because
Yes.
if we go like, if the state is like, and then if it's, if it is not deep, we have many states, and then there
Yes.
are,
Okay.
the one is small, so.
All right, so you're arguing if you have many electrons per cell. You're arguing about whether this distinction is important or not in general. Whatever it is, if you have an even number of electrons, if you have states that are completely filled,
And if it is heavy, like if it is far away from the core state.
Well, the heavier it is an atom, the deeper are the states typically,
Yeah,
because
yeah,
the larger is the...
yeah, the core is down, but the valence state is abscess, so...
Well, take a transition metal. Transition metal is a typical example of a system with many electrons in the valence state and some electrons that are borderline. Okay, take iron, for example. Electronic configuration of iron? All right, so wait a sec. Let me try and 2s2, 2p6, 3s2, 3p6, 3d10, right? Yep, correct. Okay, well, all right. So, this is clearly core state. Several kilodecadron. I would say up to this point, they are clearly core states. These states here are, I guess, of the order of 50 to 100 electron volts below the vacuum. So they're borderline. This is 20, 10, 20. This is 50, and this is 100, I guess, roughly. So, well, you may argue that it's not obvious whether I should consider them as core states or not. You can put them in, but they will contribute with an even number. So it won't change your considerations about the last valence states, because whatever you do, you're adding even number of electrons. So if it's odd, it remains odd. If it's even, it remains even. Right? So, yeah, okay. The only difficulty could be if these states were heavily hybridizing or intermixing with the 3D states when you place them in a solid. Of course, in that case, you would have to consider that, well, you have a total of 18 electrons to play with. They are not. I mean, in a number of cases, you can still assume that these are quite localized in terms of atomic states. So they clearly form bands that you can identify. These are the bands originating from 3s and 3p, and they are completely filled with 2 and 6. So they're not core states, but they are still localized in terms of bands and completely filled. So they're not particularly harmful. In any case, they contribute with an even number of electrons. So you just need to look at the last one, because all the other ones will be even. So it doesn't change your considerations.